Hey everyone, I'm Shivraj Babur, and today we come up with a very interesting topic, 32-bit Vedic multiplier using RTL to GDS flow on the open source tools. So now let's see how we can implement this RTL to GDS flow of 32-bit Vedic multiplier on the open source tools. So first of all, I want to list down the all the tools which are we are going to use in this entire flow. First tool is that Icarus Verilog and GTK Wave. So Icarus Verilog and GTK Wave we are going to use for the functional verification. The Icarus Verilog we use for the compilation of Verilog code, and GTK Wave we see the waveform of our Verilog code. So this coming to the second tool is the USS. So for the logic optimization and synthesis, we use the USS tool for its purpose. The third tool is that OpenESTA, as we have timing and power checks. So both timing and power utilizations can be estimated on the OpenESTA tools. For the physical designing, we are going to use the OpenRoad tool. So now see how we are going to use these tools from RTL to GDS. So look at our PC. So I'm now opening the WSL, which is Windows Subsystem for Linux. Is showing some documentation. So we clear this all these things. So I have kept my all these codes in one file. So I'm not going to write all the 32-bit Vedic multiplier RTL code in this video because I have already designed that 32-bit Vedic multiplier. Now I am only going to implement that to go to that directory where our all the files are located. Here we can see that uh, here my functional verification file is located, logic synthesis file is located, physical design file is located, and obviously results are there. I have implemented this flow before that, but I will show you that how to implement this flow again. So for the functional verification, we have to open the functional verification folder. Functional verification folder. Half adder, full adder, 32-bit Vedic, 32-bit ripple carry adder, 16-bit ripple carry adder, 4-bit, 8-bit. It is This is the VCD file. So now remove this VCD file, RAM VCD. So we have all these Verilog files kept in. And this most important file is that test.v, Vedic 32-bit test.v. So let's see how we can run this. So iVerilog is used to compile all the Verilog return code. So write the iVerilog -o and then write the output file name. I'm writing the Vedic 32 VVP. Now add the every file. Every file you have to add and hit the enter button. Now you are going to see that here Vedic 32-bit VVP file is ready, and here we have to use the command VVP and this result here. Okay, this is I think something is in hexadecimal. So let's see, open the GTK wave Vedic 32-bit. So it is now opening. We have to see that. Okay, see that you are going to you are going to see here that the all the output and input, these are the two inputs and this is the product as the output. What is coming? Let's now calculate the calculator. So now see the now see the our output with verified version. See here, this is exactly coming correct answer 1192464. Here we can verify that our written Verilog code is a correct Verilog code. So now move ahead with our logic synthesis and optimization. So now let us move ahead with our logic synthesis operation. So for the logic synthesis operation, you are going to need the two more files. The first is the NAND gate library, and the second is that your Tickle's flow script. Let us just see what is a Tickle flow script. Read. This is the command by which your all the Verilog files are fed to the USS tool. Then these are the commands which are essential. This is optimization command. Here are some library commands. These are some statistical commands. And finally, you have to write your all this Verilog code into the netlist step by step. Okay. So see that first of all, if I have to the USS by using command USS. So we are invoked the USS, and you have to do what you have to do. You have to just simply copy this command. Okay, here what is saying is that executed Verilog file a half adder parsing Verilog input from half adder.v to AST representation, then generating RTL-IL representation for module HA successfully finished the Verilog front end. So it is basically meaning that your half adder Verilog code is fed successfully to the USS tool. So now let's move ahead with our next command, the tool that, yes, this is my top hierarchy. Yes, here you can see that the hierarchy. Then use the probe command, to translate processes to netlist. Then clean command, it removes the unused wires. Here we are going to selecting only one module 32-bit by 32-bit. So here, yes, here you can see that it is the whole schematic of our 32-bit Vedic multiplier. Our next command is opt command. Opt command is generally used for the optimization of the our design. Share ratio. So I will attach this all these commands and resources in my description. I'm just putting the all the commands. These are some library commands which are very essential for the netlist generation. So now we can see the our total area of our design. Here we are see the total chip area of for the top model is 11734.85. Here you can see individual chip area as well. These are the individual chip areas of the design. There are different individual chip areas. Now see, let's move ahead our final step to generate netlist. Yes, this is our final step to generate our netlist dumping model. And yes, and finally we are successfully generated the netlist. Let's see, we have successfully generated the netlist. We are done with our functional verification. We are done with the logic synthesis optimization. We get the netlist from this usage tool. So now let's move ahead with our timing and power checks. Here we have library file. First of all, for the checking the timing and power, we require the library file. We require the netlist file, which is generated from the logic synthesis. And you are going to require the testicle file for the flow script, which is flow script. And the fourth important thing is that you require the .sdc file. .sdc file is synopsis design constraint. So these four things are going to be very essential to run the timing and power checks. Okay, so first of all, we have invoke OpenSTA. To invoke OpenSTA, we require the command esta. So here we are in successfully invoked the OpenSTA tool. So what the first step after invoking, we have to copy this command and paste it here. It will give the one. It means that yes, I have accepted that this library file. Then I have to feed the netlist file to the STF file. It is also successfully fed to the tool. Now we have to link the netlist file and library file. Yes, it is also successfully linked. Okay, let me link the let me feed the constraints, synopsis design constraints, and let's see, check our max path delay. Okay, something is incorrect here. Okay, here you can see the max path delay of our design. This is our max path delay. Okay, here you can see these are delay are calculated by using the library file, and finally you are getting the slack of 3.1 nanosecond, which is a standard unit which is a present in the library file. So let's see. Okay, clear command is not working here. So now let's see the min check. Okay, min check is also coming 3.01. Okay, come to the power estimation. To check the power of the design, or to see the power, we have to use the command report power. So we are going to use this report power command and see that how much power we consume in this designing. So see that here the internal power, switching power, leakage power, and total power. So as our design is totally combinational design, we don't have used any sequential part in our design. So there is the no sequential power is consuming. So there is a zero sequential power. And as well as we have don't use any clock. So that here is only also zero clock power. We have only combinational power. So here you can see here is a 9.81 into 10 to the power of minus 2 watt internal power consumption, which is about to 69% of the total power consumption. Switching power consumption is 4.228 into 10 to the power of minus 10, which is also come around 30%. and leakage power here is 6.35 into 10 to the power minus 4 is 0.4%, and total power is 1.42 into 10 to the power of minus 1 watt we are consuming in this design. So this is all about the total power consumption. So we have calculated the timing of the max path and min path as well as power estimation. So this is the and this is the final step of our OpenESTA tool. So now let's move ahead with our physical designing. For the physical designing, we are going to use the open road tool. For using the open road tool, we have to come out from this tool, and let's move ahead with our. So come back from this file. So we have successfully completed the functional verification, logic synthesis, and the timing and power checks. So for the physical design flow, we have to use the open road tool, and for the open road tool, we have to use the command open road GUI to see the interface of open road. So let's here come to the we are coming to the open road GUI, open road environment. So here we are going to implement our physical designing. Here we are going to see that our designing. So let us see how we can see the designing. You can see that I have helpers.tcl is essential file in the GCD. Here source file flow.helpers is also essential file to run the physical designing. Then you have to give the some library sources for the physical designing, left files. Then you have to set the design name, whatever design name you have to set, you have to set that. You have to set the top module, you have to set the netlist of your file, netlist of your design. You have to set the constraint of your design. You have to set the die area and core area of your design. And here we see the total flow of the physical design. We can run this file to see the our output. Okay, roll GCD. Okay, you can see here that this file is running successfully. Okay, you have to come out from this file. You have to open the open.gui, and I have some limitations on my tools because my tool is not working properly. I find that the workaround for this problem. So I used to see output like this. This is the our floor plan output. Yes, here we floor planned our output. Okay, this is our floor planning. Here you can see the ports. Here you can see the some lines. Yes, these are power lines. These are ground line. See, these are the some ports, input ports, output ports, which are generally placed not according to our design. So we close this design, and so we are done with our this step. We have to run the power delivery network. So we'll see that how power delivery network is designed in the open road tool. So that invoke the open road. Okay, completed. This flow is completed. Okay, this flow is completed. Now what we have to do, open road GUI, we have to open it, and then again see the OpenDB results, and you have to check the .odb file. And not only .odb file, you have to check that repaired route equal .obd file. In this file only you will find that the exact and correct output. Okay, here you can see that we have completed our power delivery networks. These are the power lines, and these are our, let me show you, these are also our power lines. These are the power lines. Yes, some of them are power lines, some of them are ground line, VCC lines. So this is our power delivery network. We have done with this file. Now we'll move ahead with our global placement. So we'll find that global placement, open the road. Okay, we have to run this using open road and gcd navigate 45 dot tickle. We have used this command and run successfully. Now it is in the process. Yes, it is completed. Now we'll see the output of this file using the open road -gui command. Now this file is saved into .db file, and you will find that in the result folder. Again you have to open this folder. Here, yes, this is the global placement for the 32-bit Vedic multiplier. So you will find that what is the difference between global placement and detailed placement. You will find that there are some instances. See, these are some instances which are placed by overlapping, but in the detailed placement you will find that different. Here they have just put it that yes, this is the some place which is suitable for this instance, but in the detailed placement they get segregated. And also in the uh, global placement you will find that these ports are get contracted, and according to the design they are situated. Now see the detailed placement pickle file. Okay, open road detailed placement. For the detailed placement, it is working successfully for the detailed placement. It took little bit time. Yes, it successfully executed our detailed placement flow. So let us see the exact output of our design. Let me clear this all these things. Open the open road GUI, open file, open DB, then see in the result we'll find the repaired route tickle.obd file. Open that file and you will see that these instances are placed clearly and separately. And let us move ahead with our next topic, which is the final uh, routing routing of the designing, and which is the final. You can see that you can see, let us just run the let us just run the flow.tickle, get it. As we know that we don't have any clock in our design, so there is no any need to run the flow.cts. Actually flow.cts is used for the clock tree synthesis, but we don't have any clock in our design. Yes, in our constraint file we generated the virtual clock, but it is not the actual clock, so we don't have any need to run the flow.cts.tickle file in this flow script, and we can safely overcome this step. So now let's move ahead to our flow.tickle file. And so now let's save this file and open road, open road this file, and it will take little bit some time. Okay, now it is generated our successfully .odb file, and here we successfully executed our RTL to GDS flow, and now we will see the final GDS file. So let us come out from this. Let me clear this all these things. Now open the GUI. Okay, here you can find OpenDB, then go to result, then go to this file, and you will see that this is the final our RTL to GDS flow for the opens for the 32-bit Vedic multiplier, and this is the final step. You can see that this all earlier you can see as in the hierarchy. This is the top module. You can zoom in out. These are all the routing. These are all logics. So this is the final step of our designing, and we have successfully generated the GDS file. So thank you very much for watching this video till this end. Thank you very much.